This video just requires a short introduction. So I had an idea in mind to build a little power supply, plus and minus output, so give me plus and minus 15 or plus and minus 12. And because linear transformers are hard to get these days, even on AliExpress they're expensive, and it's not common to find switch mode power supplies, small ones with a positive and negative output, I thought I could make one out of salvage parts. And you know what? I thought after the last video I could make one out of a battery charger. So okay, we know a battery charger is only a positive supply rail, and I thought, hey, you know what, I can make a plus and minus supply rail out of this. So I had a go at it. Nice little project, and this is like reminiscent of stuff I was building when I started as a teenager back in the 70s, building little projects, and they usually didn't work. And you know what, I build little projects now and they usually don't work either, but I'm a bit more experienced now and I can get them to work. I can find out what's wrong with it. So this is morphed a little bit. I think now it's a really nice little beginners video. This will teach you a few things. One is the advantages to be gained by building little projects like this, and two, this involves some basic fault finding. It uses the grounding of electronics, which is called Ohms Law, but there's not much maths in here, very little maths. I dislike putting maths in videos unless I have to, but I think you'll learn a few things. I think this will teach you some very important basic principles if you're a beginner at electronics repair and electronics in general, and if you're more experienced, I think you might well enjoy it anyway. So here goes. Hopefully it's not too long, but you never know with me. And my videos, my idea of not too long is some other people's idea of an epic, but let's see. Hope you enjoyed it, and I'll see you all soon at the end, or should I say soonish. Hi guys, welcome to another Learn Electronics Repair video. I was at the car boot sale this weekend, and as well as finding an interesting retro PC, I was looking out for some of these. So those of you who watch the channel regularly will know I made a video repairing a battery charger like one of these. And during that process, one of the things I discovered is there's a transformer in the one I fixed, the linear transformer, that had a centre tap, and then it had a pair of red wires and a pair of blue wires. And the pair of red wires was giving about plus or minus 12 volts AC. And the pair of blue was giving about plus or minus 6 volts AC with a centre tap, as I mentioned. So those sort of transformers are really useful. In particular, if you want a plus and minus supply for an op-amp based project, if you like building little gadgets and projects, which is one of the things I've been doing recently. I've kind of rediscovered the interest in doing that, yeah. And those little transformers are a bit hard to get even on AliExpress. They're not cheap, you know, there seems to be old stock around, but they're not cheap. So I thought we could use the transformers out of these things to make little power supplies. Hopefully regulated power supply, maybe a fixed plus and minus 9, plus and minus 15, something like that, or plus and minus 6, plus and minus 12. Or even variable power supply if we so wish. So you won't get a lot of current out of one of these. I mean, it's not going to provide a lot of current. This is telling you it's 6.5 watts. This one is telling you the output. Oh, this is only a 2.5, it only does 2 batteries, so this is probably of no use, but we can look inside. It's up to 250 milliamps, but it's enough for powering little projects. I've got in mind the little milliometer project that I have working. I just want to finish, put it into an enclosure with a transformer and a regulated supply. So if you were looking at this, you'll remember on the video, effectively the power supply inside the transformer gives 2 positive outputs. So you have a positive output supply on each side of the charger, which will do with a pair of AA or AAA batteries, or will do a PP3 and 9 volt battery. So you might be thinking, well, how do we get a plus and minus volt supply out of a transformer that's giving two positive supplies? Well, it's actually quite simple. So let's open these up first, see what we have inside them. And then let's just draw that out on a bit of paper, what we're going to do. If you're a beginner and you're not sure about this, you'll very soon understand how to get the plus and minus supply out of the transformer. So I'll open these up and let's see what's inside them, and then let's see what we can use. I've just turned this one upside down, by the way, and realised it actually does power 4 batteries, but it doesn't do the PP3. So this may only have effectively a single voltage rail. The 3 chargers, which I have no idea if they work, but I don't actually need them as chargers. The 3 chargers, she wanted like €3 for them, and in the end I wanted to give her 6 too, but she wanted 7, and because I wanted to do some interesting projects with them, I thought €7 was okay. I mean, the transformer itself from AliExpress would probably cost me that much to get the linear transformers, and I'd have to wait a month or more while they arrive. Actually, just before I do look inside them, let's just try them. Let's just switch them on. So I'll connect them to my current limiter just in case there's a short in one of these. I don't want it to go bang, mostly because it'll just trip out all my computers and cameras. Yeah. I'm sure you'd find it interesting. But anyway, I'll just put my current limiter on. I'll move the camera where you can see it on top of the variac there. Sorry, this is in the way a little bit. Magnifier. And we'll try it. So I'm on current limit. We'll plug the first one in. I would imagine, because these are such low power devices, it probably won't even light up at all, yeah? So that didn't do anything, but there again, maybe it won't. Maybe these just come on when the batteries are charging. What's this one do? Okay. Doesn't do anything. Yeah, it doesn't seem to draw any current. What's this one do? But I'm not surprised, because it's just low power things, yeah. Test. Okay, they don't seem to be doing anything. Normally, you should be careful opening up bits of mains powered equipment in case there's any capacitors in here holding a high voltage charge. I don't think we have a problem with these because the light bulb never even came on, which suggested power didn't go in. If the capacitors are charged, if they're there, it would kind of come on for an instance bright, then go dim. But if the capacitors are small, it might not do that. It might not light up at all visibly. Okay, smaller capacitors can give you less of a zap, but a zap is a zap, and it still isn't pleasant, yeah? Personally, I think these are probably linear power supplies like the other one I had a look at. But let's have a look. So we'll open this one up first. Let's see what we have inside it. Okay, a bit stiff. Okay, so it has what we want. It has a linear transformer. Yeah. Does it have a centre tapped output? This is the question. See if I can actually get it out of here. Well, we have, from what I can see, just trace the wires. Well, this is interesting. Yeah, we have a red wire and a black wire here which goes down to the mains. That's your mains coming in. Yeah, and then it looks like it has 4 wires on it. See a pair of yellow, a red and a black. So we can have a look to see how that one's wired up. So that has one linear transformer, but it's not quite the sort I was looking for. Let's have a look at the other ones. This has some weird sort of screw in, like a top secret safety type screw there. Can you see there's like a little, I'll show you what it has. It has one of those. I honestly don't see the point of these stupid things. I will call them stupid, because you get like a little screwdriver kit like this for like €5, and you'll have something in here that just does it. So why? Yeah, what's the point? Yeah, it's not like the restricted technology. You can't just buy the screwdrivers that undo them. You see what I mean? Okay, so that's out of there. This one is saying effectively, so it has DC 4 times. which is 4 batteries, I think, and it's saying 200 milliamps, and then it's saying DC 4 times 66 milliamps. This is the current that the batteries are drawing. This is the charge current, I'm sure. So this will be for AA batteries, and this will be for AAA batteries. Yeah, and then you have DC 2 times 9.8, 15 milliamps. But I don't believe that is actually the limit of what the transformer can deliver. I think that is actually the charging current. So we'll have a play, we'll see if we can figure out how much power this transformer can deliver. So we'll take this one out of here. This is what I was looking for. So it has 2 white wires, it has 2 red wires, it has a black centre tap. And this is quite a chunky transformer. So I'm sure this can deliver more power than it's stated on the charger. Yeah, this will make a nice little dual power supply, I'm sure. So we have that one. Let's open the last one up. Oh, again, it has these high security screws. Yeah, you need a KGB screwdriver or something to get inside them. Yeah, here we go. Somebody commented on the video, the one about reverse engineering. That one, yeah. That I am an INTP, and I didn't know what an INTP was. INTP personality, and you're right, I am one, yeah. And that in itself probably tells you why I am offended by these screws. Yeah, because they're just illogical and pointless. Yeah. Okay, so this one doesn't actually want to come apart easily. There we go. Has another fairly chunky transformer in it, so same sort of size as that one basically. This one's on a PCB mount, so this might actually be quite useful to us. Yeah, it has 2 pairs of diodes. It has 4 output connections on the transformer, so we can have a play with that one as well. Let's see what this actually does. Yeah, you know, that actually looks like a light bulb rather than an LED. Can you see it? Yeah, that actually looks like a filament bulb. Let's have a look. That's a filament bulb. Why? Why? Switch on it as well. Okay, so we have our 3 power supplies. Yeah, we can figure out how this one works. It's fairly simple. But I think the easiest one to play with first is going to be this one. So let's build ourselves a plus and minus power supply. Let's have a look to see what voltages are coming out of our transformer then. I've got the Kaiwitz meter again. I put the rechargeable batteries in that I charged off the other charger that I fixed, yeah, just to show it did work. So we'll just go to volts and we will select AC. We'll switch it on and let's see what we have. So if we go from the black wire, which will be the centre tap or ground effectively, to the red ones, if we just get a connection up, bent to the end of the meter probe. So if we go from the black lead, which is effectively ground, we see we have 3 volts on this one. 3 volts on this one. It's giving me less than the other transformer. And let's have a look at what we have here. 15 volts on that one, and I'm saying the same on this one. Yeah, plus and minus 15. It looks like plus and minus 3, which is rather lower than I hoped for. So that's what we have. And then you can see by these ones there's some rectifier diodes. So if we go back into DC, again we'll go to the black lead and we'll check on the diodes. So we have an 18 volt supply, another 18 volt supply. So we know the transformer is working, so let's take this apart now. Let's get some of the parts off it that we're going to use in our project. There's a few useful bits on this. I mean, we have the rectifier diodes, and we have some more rectifier diodes here. So I'll take those off, they can be useful. Looks like we have a couple of transistors, so we'll have those. The LEDs are always useful to have, so we'll take those as well. Then I'll get these connectors off because underneath here is a chip. You see this thing here? This thing is like a single in line. It's probably an op-amp chip, so that might be useful. Another transistor. So I'll get the useful bits off here, then we can get on the bench and let's see what we've got. And I'm sure we can use some of these parts in our project. I've taken all the parts I was interested in off here. There are some little diodes as well. Yeah, I mean, it's possible even one is a Zener diode, but I have lots of those sort of things. So this is what I actually have that I thought was interesting off here that we can use, and some of this we can use in this project. So we have a little switch, an on-off switch if you like. I like this. So look, you can see it's just a double holder for PP3 batteries, but you know, if we connected those two together and put a ground wire from here, we could have a nice plus and minus 18 volt supply from two batteries. Yeah, how simple is that? We have a chip, but somebody scratched all the markings off. What is it with these battery chargers that people scratch all the markings off? Are they like top secret designs or something? We'll look at that under the microscope. It reminds me of some op amps that are in this package, like a single in line like this, but we'll see. 3 LEDs are always really handy, so I'm sure we can probably use a couple of these in this project. And these rectifier diodes, we'll definitely use these because we need some rectifier diodes anyway. We can have a look to see what they are. 1M400, 1 amp, 50 volts. Same, we can use these 1 amp diodes. Yeah, oh, I think they're probably all the same. So yeah, they're going to get used. At least 4 of them probably get used. Yep, same. So a handful of 1M400s. Yeah. A resistor that just came off, it fell off. I don't really want it. And then we have a few transistors. So, or are they voltage regulators? We'll have a look, yeah. So we can have a look at these. Are little 470 mic 25 volt capacitor. Don't really need it. Let's have a look at these transistors and then let's measure our transformer now we've taken this off the board, and let's figure out how we're going to put this together. Yeah, we have SD965. These are all the same. Was that a 985? No, 965. They're all the same. We can test one. Probably little NPN transistors. 2SC 2785. Looks like a 2SA. There's A1175, I think. Yeah, we can check them on the component analyzer. I'd say these are an NPN and PNP, and those are all the same. And then the last one is this little thing, which somebody has scratched the markings off. Let me see if I can actually see it down the microscope. I think we can probably read this one. I'll get the torch. Looks like ANC, possibly 789 or something like that. No, it ends with a 2, I think. I'm sure it's ANC and then 7 something 2. So a little bit of ISO profile. Might be a bit less on this brush. No, it's dry. What's he doing? There we are. See if we can figure out what it is as this dries up. Let it dry out a little bit and so see what it reveals. Yeah, here we go. A bit odd to read. ANC could be a 7 or a 3. Looks like an 8-9 or 8-0, something like that. We don't need it, but I thought some of you guys might be interested to figure out what that actually is. Okay. Because we salvaged these diodes and this thing possibly wasn't working, we probably should just actually check them first to make sure they're good. You can just do this with the multimeter if you like, or you can just use the component analyzer, doesn't really matter. So that's a good one. And I'm pretty sure all these will be good, but we should check. Yeah, you can do it this way, or we can do it with the multimeter, whichever we prefer. Yeah, go into diode mode, and it'll conduct in one direction. We probably don't need to test both directions. If we see a diode junction in one direction, we can assume it's good the other way, in the other direction. Yeah, let's have a look. Nothing that way. So the black goes to where the stripe is, basically. That's a diode junction. Have a look at this one. So we've got some good diodes here we can use. Yeah. Yeah, it's a good one. We could test the transistors, at least that the diode junctions are okay with the multimeter, and see if they're NPN or PNP, but in this case it's probably easier just to do it this way. So we'll just stick them on the component analyzer. We don't need these transistors. I just thought you might be interested to see what we actually have, and we can stick them in our stash of bits for future use. Okay. NPN silicon transistor, quite a high gain one. So that's one of the SD965s. Let's just try the other ones. So my guess of being an NPN transistor is probably a 2SD965, I'm guessing. Yeah. Last one of this type. Low battery. Yep, that's a good one. And then the other two, I'm pretty sure, is a 2SA and a 2SC. So one's going to be NPN and PNP. I think the 2SA is the PNP, but I can't remember without just looking it up. But this will certainly tell us, yeah. Well, this will tell us all right. So I have to put some batteries in this. That's a PNP, yeah. That's a PNP. Is this a 2SA? Yeah, it is, and it is a 2SA 1175. And then this, you'd imagine, is a complementary, probably NPN, so the same current and voltage ratings, just the opposite polarity, if you like. NPN, PNP. Polarity isn't really the right word, but I'm sure you knew what I meant. Yeah, an NPN. Okay, so we have those. I don't think we're going to use them in this project, but we have them. Let's have a look then. Now we've disconnected the transformer. Let's power this up and let's measure the voltages that are coming out this once it's disconnected from the PCB. I've unsoldered the transformer completely. I'm just going to put a terminal block on and some wires. Just bear in mind, guys, high voltages can be dangerous. Obviously, with electronics work, especially power supplies and such like, there's going to be high voltages. So This is one of these cases where if you understand the dangers and you respect them, you are pretty safe. Especially on my workbench, because I actually have an isolation transformer, which means I can accidentally catch hold of either the live or the neutral, and I will be perfectly fine as long as I don't catch hold of both of them at the same time. Okay. If you wanted to be safer, you could put some insulation tape over this, or use effectively like an inline coupler, so the thing is basically covered. Do this however you are most comfortable with, which will no doubt depend on your experience level. I'm okay with this, quite accept that some people will not be, and some people will probably tell me in the comments that I shouldn't be either. Okay, so we have our transformer. Now before I actually plug it in, let's measure the resistance on this so we can see what we actually have. The first thing you'll notice, the red wires are a bit thicker than the white wires, which would suggest that they take a higher current or can supply a higher current. Yeah, normally thicker wires means a higher current. I put my meter on ohms range, and the black, this is the center tap, so this is effectively the center of the winding. So what we should have here is a connection from the red, each of them, to the black, maybe with a little bit of resistance, depends on the winding. So that reads almost zero, but transformer windings can read very low, almost zero, almost zero. So we can draw this on a piece of paper. I'm going to measure to the white ones as well, so we can draw it all in one go. So if we go from the black again, that's reading 9.6 ohms. That's a higher resistance winding. Now, that could be because it's a much higher voltage, but it could also be because it's a much lower current winding, so it's effectively thinner wire. Well, basically we have a transformer. So on one side is the primary. This is going to the, in my case, 220 or 240 volts AC. And we have the secondary. Now the secondary, this is the two red wires. And they have the black wire in the centre. So I'll draw the winding on the transformer like so. That's the two red. And then the centre of the winding has a tap on. And this is our black. Okay. The two white wires are also connected to this winding, and they're either giving more or less voltage than the two reds. So they could be tapped off from here and here, giving a low voltage, or there could be additional windings giving a higher voltage. So let's have a look to see what they're actually doing now. So to measure them, we need to go to AC volts. So I'll choose volts, one touch of the button, volts DC, select volts AC. So I'm on volts AC. Now the thing with these transformers is the two windings I've just shown the drawing are completely isolated to each other, or I should say are completely isolated from each other. One winding, the primary, is in this bobbin and the other ones are in this one. So there's no electrical connection across the transformer, primary to secondary. This is your primary voltage in, secondary voltage out. So it's quite safe to touch these, yeah, where it's not safe to touch these. So we'll switch it on, and then let's have a look what voltage we have. So we go to the black one, and I can use my fingers, this is perfectly safe. This, as we read in the circuit, about 3 volts. Yeah, 3 volts, okay. And then the white winding is a much higher voltage. 15, yeah. 15. So the 3 volts we read in AC on here maybe will give us 5 volts DC, because DC is a peak voltage, but this is probably too low a voltage to be useful in our circuits, but we can have a look anyway. And this plus and minus 15 is a very useful voltage for op-amp circuits. So let's figure out how we're going to get a plus and minus voltage supply out of our transformer. Here is our diagram. So we can continue with this first. We know the white windings are giving more voltage. So what actually happens with our transformer is the white is here and another one is here. So basically with a transformer, the output voltage depends on the ratio of the number of turns in the winding. So basically the primary will have a much higher number of turns than the secondary. If you say you had 1,000 turns here at 220 volts AC and you had 100 turns on the secondary, you get a tenth. So you have 220 in, 22 out. That's basically how it works. So we know the white ones are giving more voltage, so they have more turns in the windings. So that's what we have. So we want to get from this positive and negative supplies, and we're going to try and get two supplies and see what we have. To convert the AC into DC, you need a rectifier diode. And the rectifier diode, we've just taken half a dozen of them off the circuit board. This is the symbol. And they pass current in one direction. Which if you imagine that's like an arrow pointing this way, it passes current that way. So in this case, only the positive half cycles will come through here, yeah? And we can put one here. This is the lower voltage, okay? On the other side, to get a negative voltage out, we need to put the diode the opposite way. Okay? And again, we're going to put two of them. So we're going to connect 4 diodes to our transformer like this. To do this, we'll use a little bit of Vero board. Let's solder this together and let's see what we've got now. We could also build this if we wanted to on a bit of breadboard. But I want to have this little power supply, so we'll do it this way. I'm not going to try to make this as small as possible. This is meant to be an educational video. If we wanted to, we could use a much smaller bit of board, but we'll use this, please. So I'll just clean this, solder off this bit of wire, and we can start to attach them. So I'm going to put the black wire in the middle, basically. Looks like I have to just clean the solder off it, but I'll get it on here. And there we have it. I've effectively put the black in the centre of the board. We can, if we like, we can just draw a line across here. Good practice just to mark it. So we know that this line here is ground. Okay, and then you can see I've put the reds just either side of the white line and the white's just either side of the next white line, so we can see quite clearly where the voltage rails are. Now there's something I just want to mention that I just neglected to say earlier, but it's important, so I'll just mention this. I was showing on the diagram that the transformer, primary and secondary, are isolated from each other. And with this transformer, I can actually see 2 bobbins in here, 2 sets of windings. So I know visibly really that is the case, but you shouldn't trust that, especially with cheap electronic devices. It's possible you may find a device with what's called an auto transformer in. Now, an auto transformer will step the voltages down in the same way, but it will not give you what's called a galvanic isolation, the isolation between the primary and secondary. Therefore, although the secondaries have low voltages on, you can still get a full mains potential shock by touching it. And I'll just show you what that is. If you come across anything like this, it really is not a safe device. So I wouldn't expect it, but you never know. So we're on ohms range. If we just measure across the primary, you'll see our transformer has about 570 ohms. As I said, the primary winding has a lot more turns in the winding than the secondary. But in any case, with the transformer, there should be no connection between the primary and any of the secondaries. So if we go across here, yeah, it should be open circuit. Yeah. I suggest, especially if you're beginners at this, just do check that before you start messing around with little mains transformers. I'll show you on the drawing what you may come across, just so you can be clear on this. So this is our transformer, but it's possible you may come across what's called an auto transformer. So with an auto transformer, effectively you have one big winding, just one winding, yeah. And across here you have your AC mains, and then at some point in the winding, it could be anywhere really, but at some point in the winding you'll have a tap, another one, another one, another one, another one, and this could be your white, red, black, red, white. And from the black, if you put your black meter probe on here, 0 volts, you will still see 3 volts to here, you'll still see 15 volts to there, and this side as well, yeah. But the voltages may be the same, 15 volts, 3 volts, 3 volts, 15 volts, but there's no isolation, you haven't got this barrier. So although the voltages between the points are all the same, every point is connected directly to the mains. That's called an auto transformer, and you really should not come across that in these sort of consumer devices, but really shouldn't, and what might happen to you are not necessarily the same things, yeah. So just bear that one in mind. So now we have our transformer connected to our Vero board. Let's put the rectifier diodes in. So we have a little stash of these taken from the charger. These are 1 amp diodes. We can assume that these are sufficiently powered to handle the current this can deliver. So let's put our diodes in. We could start laying them flat and cutting tracks, but I think I might just do it the easy way if they're long enough to do it. So let's see. Yeah, we can fit them in. So we put one here, and that means on this will be our DC output. You see I'm putting the diodes with the stripe towards the voltage rail I want to generate. This will generate the positive voltage rails, yeah? So we have there, we have there. Now on the other side we want to generate the negative voltage rails. So in this case it goes the other way round. So the stripe goes towards the AC coming in, basically. That way. So it's the opposite way round. You can see the opposite way round. And then we want more. That one was too short, but this one's just the right shape and size. So this can go on the other voltage rail. Okay, so we'll put our diodes in. I'm just going to straighten them up so they're in the same position on each one. A bit tidy because I'm a little bit OCD, to be honest. Let's solder these in place. Okay, that went quite simple. I hope it was in shot and you could see it. Let's test this now. So let's measure what's coming out of this, and then let's look on the oscilloscope. I want to show you what this is actually doing, yeah? Here is our voltmeter. We now want volts DC, and we're going to measure what's coming out of each of these diodes. I'll probably have to turn it upside down to actually get on them, to be quite honest. Yeah, I can't get to the back end of these ones. Okay, let's do it. Black we will put in the middle, the centre tap. This is our ground. And then we have, on this diode coming out, 2.3 volts, yeah? 2.3 volts it's reading. This one's only reading about 3.6 volts at the moment, yeah? Yeah, you might be wondering why. -1.3, And you'd expect it to be the same as the other side, but it's actually kind of a bit all over the place. The meter doesn't seem to like that very much, yeah. This is kind of doing the same thing now, yeah. And this is giving a steady reading. Let's put our oscilloscope on it and let's see what it's actually doing. I've attached a couple of header pins on this side so I can easily get to this side of the diode without turning the board over. I've also soldered one in the middle so I've got a ground point for my oscilloscope or test meter. So we can have a look now. So this is what's coming in on the low voltage winding, and you can see we have AC, and we go to the other one. Can I get to it? We have an AC signal, yeah. What comes out of our diodes? DC. Well, what actually comes out is this. So you can see effectively we're getting the negative half cycle. The bumper that's going below the center point. Center is 0 basically, yeah. And if we go onto the other diode, we're getting the positive half cycle, you see it? And on the higher voltage winding, if we just go to the winding, we have a much higher voltage AC. Yeah. Same on both ends of the winding. And coming out of the diode, well, there's a much larger negative half. Yeah. And a much larger positive half. Now, if you look at the one in the middle, the low voltage, you'll probably see that, can you see that bump isn't half of the voltage? Yeah. It's kind of like less than the top half. That's because this is only a low voltage rail, and when this diode conducts, effectively it loses 0.6 of a volt. So we're only getting a bit of a bump there, yeah? And the same with this one. When we look at the high voltage, the 0.6 of a volt has less of an effect, so we see pretty much the whole half cycle. So there's a couple of things we can do first with this. First of all, we can solve this problem, or rather mitigate this problem where we've seen only a small part of the signal here, yeah? And secondly, we can then add some smoothing capacitors to get a proper DC voltage. So let me show you how we're going to fix this problem with this being a low voltage pulse, not half a cycle. To get around this problem, we're going to fit what's called Schottky Diodes. So this is one of the 1N4001, same as we have it. And you can see that is the forward voltage drop in diode mode. Diode mode basically measures the voltage drop, not a resistance. You see it's 0.567 volts. So that's how much voltage has dropped across this diode when it conducts. That's why we're not seeing the entire half cycle coming from the secondary. And it's notable on the low voltage one. These are Schottky diodes. These are 2.5 amp. They're just what I happen to have. And if we look at one of these and we do the same test, forward voltage drop is 0.18. So it's much lower. So this means more of our half cycle voltage will come through the rectifier, which is what we need. So let's take out the two from the red windings and let's fit these instead. I've changed the diodes. Now, this can confuse beginners, because it confused me when I was a lad, yeah. I used to think that if I connected my electronic project to a car battery, which was like 12 volts, 80 amps, that it was going to cause the project to explode, because my project couldn't handle the 80 amps, yeah. This is before I understood Ohms Law. So with these diodes, just because I say they're 2.5 amp diodes, it doesn't mean they will provide 2.5 amps. It just means that they have a maximum rating of 2.5 amps. That's the maximum they can deliver. So these are actually 2.5 amp 40 volts. These are 1 amp 50 volts. The 50 volts again is a maximum rating, so it doesn't need 50 volts to work. It's just the amount it can withstand. We know this is about 15 volts, and this is about 3 or 4. So that is not a problem, yeah? That is fine. Let's connect our oscilloscope again, and let's see what it's doing now. So I'll just connect the ground lead. We'll switch it on. Okay, so AC half a wave, AC and a kind of half a wave, yeah. That's the other higher voltage one, AC output, and this is the other one, the low voltage one. We get to it, AC, and the same thing. Okay, it's kind of mostly given as a positive half cycle. This is all about experimentation after all, so that's interesting. It's like this, we were seeing effectively what I expected, the positive half cycle. Sorry, this one, the white one, positive half cycle. And then on the red ones, we were kind of like seeing the positive and then a little bit of the negative. If this we consider to be 0 volts, yeah? And it was doing the same on the other side, so basically the red one was giving us a kind of a voltage that was going to be positive and then with negative. Again, 0 volts was kind of here, and then this was effectively just giving us the negative half cycles. Yeah. Now, this is a kind of a pulsed DC, it's not a smooth DC, which is what we want. So as I just mentioned, to fix this we need to put capacitors on here. So what we're going to do is we're going to connect from the red, this is the positive supply, so this way around electrolytic to there, yeah? And then from the white we're going to do the same thing. Yeah? That will give us a smooth positive supply here, and the capacitors should charge up to the peak voltage, so I'm expecting to see more voltage here than we had on the AC. The AC being effectively the average of the signal, yeah, the average, the root mean square, we'll call it the average voltage, yeah. So that's what I'm expecting there, and the same on here, I'm expecting to see the peak voltage. This side is our negative supply, so the capacitors go the other way round with a negative to the voltage rail, yeah? Just draw them in, put some dots in, and again with this one going to the higher voltage rail. Okay, so what we should now have is a plus and minus supply. The value of the capacitors isn't particularly critical, and if we're not getting enough smooth and there's too much ripple, we can just put 2 in parallel. So I'm going to put in here, just because of what I have, 2200 microfarads at 16 volts, because as we know this is quite a low voltage rail. It may even be too low for us to use, but we'll have a go. And then here I'm going to put 1000 at 25 volts, because again it's what I happen to have, and we can always put, you know, more in if we need them, we may well do, but this is quite a low current supply, so let's try that to start with. I've fitted the capacitors here, so these are the positive output rails, the ones with the stripe of the rectifier diode going towards the voltage rail, so positive end of this capacitor, positive end of this one. These are the negative ends, so it's the anode of the diode going to the voltage rail, so negative, negative. And then basically the 2 positives of these and the 2 negatives of these are all connecting to ground. So we now actually have a ground rail in a few places on here, so I'll draw them in. It just means we don't make any mistakes later. So this is actually a ground, and we have here a ground, and the same here. And we can always cut the track to, if we want to use this track further on not connected to ground, but if we draw them in now, it makes it less likely to make a mistake, you know, when you're doing this sort of thing. You've actually, you know, you're putting this together on the fly, yeah, making it up as we go along here, basically is what we're doing. So that's that one. pen doesn't seem to be working very well, I guess. I mean, I've had these a long time, so there we go. Right, so we should now have 4 DC output rails. Let's see what we've got, and let's see whether the low voltage one is any use to us. I'll do this now from underneath the board. I don't think we need the oscilloscope right now. We can check for some ripple on the voltage rails once we put a bit of a load on it. But let's have a look. In fact, we'll check them anyway. So we'll power our power supply up again. Okay. Put the voltmeter on. Well, let's see what voltage rails we have. So we want volts DC. This is ground in the middle, and I'm going to measure under the capacitors. I took the links out because I don't really need them anymore. So ground is here. So we have a 14.3 volt supply, and this should be the minus 14.4 volt supply. Okay, and then on the other capacitor, this is a minus 4 volt supply, and this is a plus 4 volt supply. Okay, we can now mark our voltages on here. So we have plus 14 volts, we have minus 14 volts, and then we have minus 4 volts, and we have plus 4 volts. These are not really of any particular use to us. It's a shame. If the transformer had more windings, we could get more volts. If we could get 9 out of these, or 7, we could make a plus and minus 5, and we can make, I think out of these, probably make a nice plus and minus 12 volts. So what we need to do now is to make sure we have a stable voltage coming out, and to make sure we have a useful voltage coming out. And I'm going to see if I can get from this plus and minus 12. Now, to do this, I'm going to use fixed voltage regulators. You could use a variable or 2 variable voltage regulators for that matter. But to keep it simple, I'm going to use plus and minus 12 volt regulators. We can check the data sheet to see if this will work. So what I'm thinking of putting in here, 7812, which is a positive 12 volt regulator. And basically this connects to ground, and coming out we have the voltage we require. We need to put some more capacitors on this to make it work properly, yeah. But the idea is to put that there, and on this side we'll have a 7912, which is a negative 12 volt regulator. We'll go like so, and we'll go like so. And I say we'll need some more capacitors on the output. So let's see if we can use these voltage regulators. I need to check the data sheet. This will tell us whether the 2 volts difference between the input voltage and the output voltage is enough. Here are our 2 voltage regulators. So we have the 7812, the 7912. The 7812 has a pin out, in as much as the middle pin is ground. The input is on 1 and the output is on 3. So this is basically pin 1, this is pin 2, and this is pin 3. And that to me is sensible, if you like. It's like the diagram. But the 7912 doesn't have the same pin out. With the 7912, the input is on pin 2, so I'll make a note of this in our diagram. The ground is on pin 1, and the output again is on pin 3, the same. It also says, this is a typical example, we need to put a 1 microfarad capacitor close to the input and another 10 microfarad close to the output. So we'll do that as well. We may also need to fit heat sinks onto these, but because this is probably quite a low current supply, then we may not. These will handle generally 1 amp up to 2 amps peak. The wattage depends on the voltage drop. Now, the minimum voltage drop is basically 2 volts, and we're pushing it a little bit with our design. So we might find this just doesn't work reliably, and may work better using 7809, which is a 9 volt output, and 7909 to give us a plus and minus 9, which is also useful for op amp circuits. But seeing as these are the ones I happen to have and I don't have the 9-volt versions, let's try it and see. I fitted the voltage regulators, positive and negative. This one, the positive one, was quite easy to fit, so the centre pin is ground, and then we have in and out. So you can see I've just effectively just cut the track here between the in and out. So this is the voltage coming in, going out, and this is one of our ground points. Now the other one is a little bit, to me, strange. So pin 1 is ground, pin 2 is in, and pin 3 is out. But it's very difficult with this sort of strip board to cut a track directly between two holes. I mean, you can do it, but it's a bit fiddly. So what I've actually done is, you'll see we have pin 2, which is in, connecting to the capacitor. This is your power coming in, and then out is on this one here. Yeah. So we can switch this on now, and we can measure the output from our regulators and see if we have what we expect, which is plus and minus 12 volts. I'll just get a connection to ground. Let's switch it on. Now let's see what we've got. So this is our 12 volt regulator here. And that has 12.15 volts on. And this is our minus 12. And that is minus 2.5. That's strange. What's on the input to it? That's pin 2. Well, that's minus 3.3. So it appears there's something wrong with this voltage regulator. The power comes from the diode here. We can just check there. Just switch it on. No, we only have 3.3 volts there as well. So let's see if we can just figure out what might be wrong with this power supply now and why we don't have the minus 12. Here is our schematic. So let's see what we've done. We've put a capacitor on here. And we've put another one on here, the other way around. So this is positive to this end, this is positive to this end, because this end is more negative than here. So we've put those capacitors in, and they are the 1 microfarad. This one here, these are the big ones we fitted. They were 3,300, I believe. And this is the 1 microfarad. And then we have another capacitor, the little tantalum ones on the output. Like so. And another one here. Again, this is the negative end to the negative. And this is the this is the 10 microfarad. And we can see the positive regulator is working, and here we have plus 12. But here we don't have, we only have about minus 2. And coming in, we only have about minus 3. So why? Because we had minus 14 here before. Why are we getting a low voltage? Well, I think it's fairly obvious, certainly if you have a little bit of experience with this, that something is dragging this voltage down. So if there's not enough voltage coming in, you can never have enough voltage going out. Yeah, something's dragging this voltage here down from this diode. And really, there's only 2, 3 ways that could actually happen, 2 or 3. Yeah. So let me just explain to you, and this applies really to any sort of voltage rail, whether it's a supply like this, or even if it's a logic level on the circuit board, an enable signal or something like that. You always have the same situation. You have the source, whether it's coming from a rectifier diode, whether it's coming from sort of chip sending out an enable signal, or a power good or something like that. You have a source, and then you have effectively the target, the destination, the load. The load, yeah. The load could just be another chip with a chip selector or something like that, whatever pin, yeah. It could be something like that. or in this case it could be something connected to here. Now, we don't have a load, but we do have a capacitor on here. Yeah, we have a capacitor here, and we have the regulator. What we need to look for in this example is paths to ground, because something is dragging the voltage down. Yeah. So which components connect from this rail to ground? Well, this capacitor does directly. Yeah. And this chip has a ground pin and an in pin, so there is internally a path to ground. Okay, but this chip also supplies the in to the out. Yeah, in, out, and on out is another path to ground, this capacitor. So conceivably, if any of these three components are faulty, be reading low resistance or near to a short, it would pull this voltage down. Yeah, these two directly and this one indirectly through the chip. So one of the possible problems is a low resistance here, a low resistance here, a low resistance here. Yeah, the same as this type of example. In this case, you would normally have a resistor which is holding this to some sort of voltage level, let's say 3.3 volts. Yeah. So normally this signal is high. We'll put a line over it, which means active low. We'll put a line over here, means active low. So in this case, what should happen is this chip should be able to take this signal low, or this should be able to take this signal low. If the signal is just low when it shouldn't be, so effectively whatever inputs on this shouldn't be generating an active low. If it's still low, you have the same situation. You could have a short or low resistance in the source. Yeah. You could have a short or low resistance in the load, because both of these chips have got connections to ground internally, so there is a path to ground in the chip. And the other possibility is that this resistor could be open circuit, so there's nothing to pull it high. Yeah. So you can see that the various reasons why this could be low when it's not supposed to be, if it's always low. So if you can understand that, and I'm fairly sure even to beginners that's fairly clear. Yeah, if there's no resistor pulling it high, it will be low. If either of these drag it down, it will be low. The same applies to our circuit. This applies to any circuit. Yeah, as I said. So there's another possibility why this voltage would be low, and it's the equivalent of this resistor. Where's the resistor in here? Well, there isn't one exactly, but this diode effectively acts like a low value resistor. It conducts. Yeah, it conducts that direction, and it isn't zero. It has effectively like a little resistance in it, a finite resistance. Yeah. Where's the current going? Well, the current's going back to ground, which is here. Yeah. Where's it going through? It's going through the coil. Does the coil have resistance? Yes. So effectively, this coil also has, if you like, an imaginary resistor in it. And if that resistor is too high, it's the same as this. Yeah, being open circuit or too high. So the other reason why the voltage here could be too low is that the source, where it's coming from, is too high. And we call it impedance. It's really resistance. The reason we call it impedance is a technical term. Impedance is resistance that varies with frequency. Yeah. So the source could be too high impedance. That means it cannot provide enough current into this circuit to make it work. The other thing is that this, with the capacitors, with the regulator, could be too low impedance. It's drawing too much current to ground due to a fault. And those are the only two reasons why you can have a low voltage. Too high impedance source, too low impedance load. And the same applies to this. Yeah, if there's something wrong with the source, effectively it's too high impedance, there's resistors open, it's too high impedance, it can't drive the voltage high, or this is too low impedance and it's holding it down. Yeah? And really, guys, this is the fundamentals of fault finding. If you didn't get it, just play that bit back again a little bit later when your brain's settled, yeah, when you've had a coffee or a beer. But if you grasp this relationship between source impedance and load impedance, you will be able to repair a whole load of stuff. A lot of stuff will make sense to you once you've grasped this. So, given that, where's our problem? Why isn't our circuit working? Well, the first easy thing to test, and this is probably the easiest thing to test, is have we got a low impedance load, a short or near to a short on the output? Yeah, so let's have a look. So this is our output capacitor, this is on the output of here. Let's measure the resistance across it. Well, it's kilo ohms, yeah, it's kilo ohms, it's high resistance, yeah. Let's have a look at the input capacitor. This is effectively the resistance across the input, that's this one, yeah. Do we have a low resistance to ground? Let's see. So this is the capacitor. No, we don't. It reads basically open circuit, yeah, open circuit. And this one's into the kilo ohms. On a high voltage rail, I mean a very high voltage rail, that may actually be a low load. But on a voltage rail of 12 volts, it isn't. And we can work that out with Ohm's Law. This is the one bit of maths I do on the channel. Let's figure out, if that is the actual load, how much current is flowing through the load, yeah? Let's figure it out. So for this we need Ohm's Law. Always remember Ohm's Law like this. And draw a triangle. V, I, R. Yeah? You can remember it. R, this is resistance. I, this is current. V, this is volts, yeah? Remember which one goes where? Easy. R is on the right. Resistance is on the right. R, they both begin with R, yeah? V is at the vertex of the triangle, yeah? If you remember that, you'll always get it the right way round. So, if we want to know the current that's flowing in our load, and we know the load's 2.4 kilo ohms or 2,400 ohms, yeah? And we know the voltage of the supply, 12 volts, it's close enough, yeah? So, we know those values. What's the current flowing? Well, current equals V over R. Yeah, that's what the triangle's for. I equals V over R. R equals V over I. V equals I times R. That's the triangle. So we can work this out. R is always in ohms. I is always in amps. And V is always in volts. Let's see how much current we've got. And I'm fairly sure you can see 12 divided by 2,400 has got a 5 in it, and it's not a very big number. Yeah. If they taught you mental arithmetic at school, they taught us how to do that. Let's see. So 12 divided by 2,400. Told you to have a 5 in it, didn't I? So this is amps. This is 100 milliamps. This would be 10 milliamps. So that would be 5. Yeah. 0.005. That's 5 milliamps. That is the resistance of the load. Yeah. If it's a linear resistance, I mean, a chip might vary its resistance with voltage. It's not linear. But we can see there's no short there. There isn't going to be much current flowing down through there. Okay. Let's compare it with the positive regulator. So this one is working. So have a look what we've got. Get the meter again. Resistance. Well, that actually is higher, quite a bit higher, yeah. And what's the resistance on the input? Well, that reads open circuit, the same as this one read open circuit. So yeah, this one is a little bit higher. But there's no shorts there. We don't have a short circuit capacitor. So, have we got a faulty voltage regulator? Well, the way to prove that is to change it. That's one way we can change it. We can put another one in there. So I have a spare one. Let's change it and let's see what happens. I've taken out the suspect voltage regulator, the 7912 negative regulator. This was a new one. The only other one I have is this one, which is salvaged from something's a pull taken from something or other. So I don't 100% know that this is good. But let's compare them. So we'll go to the ground pin, I think, on pin 1. I'll use the positive lead because it's a negative regulator. And let's just check the resistance. So that's the resistance to the input. And it's about 16 meg. And this is the resistance to the output, about 5.6k. Yeah. What's this one reading? Well, that's effectively open circuit. And that's 22k. So they definitely read different, yeah? Let's look at these middle pins. That's 2.37. What's this one? 1.7. So they definitely read different. Does this mean we have a faulty one? Let's just try diode mode and let's see what that reads. I mean, there's no real way you can test these without actually connecting them up. But let's compare them. Comparison can sometimes be good. So again, we're on diode mode now. Well, that's reading 3.27, 3.0, 0.56. Yeah. What's this reading? 2.2, it's lower. 2.2, it's lower. And 0.54. So they read different, but you can say that, for example, those two are both giving a low reading. It's just one's a lot lower than the other. No, they're very similar. They're very similar. It's the other ones that read differently. 3.27. 2.69. So this reads lower. Now, bear in mind these are not the same make. This is an SGS Thompson, and this one is on semiconductor. So, although they're both the same device, they're not the same make. So, it's possible the difference of readings are just some internal difference, but they both work the same. But because you read different, let's put this one in our circuit and let's see what it does. Just before we do that, let's measure these capacitors as well. So this is our capacitor on the positive voltage rail. And that's reading about 2 volts on the diode range. It's climbing up. It's obviously charging. The capacitor is charging, yeah? Okay? It'll probably eventually charge to the point where it just reads open. Okay. What's this one doing? So this one, this is the positive end. This is the negative rail. Well, that reads low. Completely different, yeah? Like this capacitor has a problem. Let's look at it. Ah, I think now we can see where our problem is with this. This is the capacitor on the positive rail, and you can see there's a little plus sign just there, plus minus. This is a positive voltage, 12 volts, and we know we drew a line up here. This is ground. So the positive on the capacitor, the terminal, positive terminal, is connected to the positive. Let's look at the other one. So the other one, you can see what I've done here is I've actually put it in the wrong way round. In this case, I've put the negative to ground and I've put the positive to the supply rail. But this is a minus supply rail, so this capacitor is in the wrong way round, and I'm sure that's why it's reading this low resistance, effectively this low voltage, and it looks like that is the cause of the problem. Now we could put it back in the right way round. Let's see what happens if I actually measure it the right way, so the red to the positive. Does it now just charge up? No, it doesn't. It reads kind of like low in both directions. So it looks like that capacitor has been damaged. This is the same thing that would happen if we had effectively a leaky capacitor with a low resistance, not short. The reason it's not short, we didn't have 0 volts coming out, but we had a very low voltage coming out. So it looks like we've actually damaged that capacitor by putting it in the wrong way round, but this is effectively the same thing that would happen if we had a faulty capacitor. Let's change this one. I've soldered the voltage regulator back in, the original one I was using, and I've put the capacitor in the right way round. This is a replacement one. This is another very important thing really with fault finding. Change one thing at a time. Because we found a definite problem here, I put the original one of these back in again. Normally speaking, there's only one component causing the fault, unless you've had a short circuit and it's blown some others. But change one thing at a time in this sort of situation. Right, let's check now. So we'll go across our capacitor again, positive to negative. And now it's reading high, yeah, it's not reading that low thing, that's on diode mode. So let's power our board back up again and let's see now if we have a plus and minus 12 volt supply. Okay, I'm on ground, let's check the minus. And we now have a minus 12, and we can go over here and we have a plus 12. So we now have the supply rails we expected. You might be wondering, why didn't the capacitor explode? Well, this really brings us back to this discussion I was having again. This capacitor effectively was acting like a near short circuit. It was drawing as much current as it could through it. But when I say as much current as it could, is because it's limited by how much current this winding in the transformer can actually supply. And we know this is a fairly small transformer. It may not even have enough oomph, if you like, to drive our device. I mean, I'm hoping to get a few hundred milliamps out of it. We'll have to try that very shortly now we've built it. But the reason is that it couldn't supply enough voltage for this to explode or get hot. So what happened is the output here was being dragged down by the faulty capacitor. Yeah, this was passing, I say a lot, compared to how much this can supply. It was passing a lot of current into here, and so the input voltage went down. This is another very important thing that beginners should learn. So when you have like a short or a similar condition, if you measure the voltage here and you find the voltage here is too low, don't think, well, there's a fault with a diode or something further back. Yeah, the fault can be the other side of something like a voltage regulator. So a short on this rail can take this rail down towards ground. Yeah, so always keep that in mind when you're wondering where is the load. Okay, so we've now got our little power supply working, fixed output, plus and minus 12. So I think the best way to test this to see is how much current can it draw is to put some resistances on the output and basically see how much we can load it before the voltage here drops. So how much load should we put in our power supply and how are we going to do it? Well, let's try for 100 milliamps on both rails first, plus and minus 12. Let's see if it can do it. So I think actually we should all stick one of these on our mat somewhere, on our bench somewhere, and we can print these out. VIR, yeah, V in volts, R in ohms, I in amps, yeah. So what do we want to do? Well, we want to put 100 milliamp load on. We know what the volts is, it's 12, yeah. We know what the current we want is 100 milliamps or 0.1 amps. So what resistance do we need? Well, 12 divided by 0.1, I think you can probably easily work that one out, is 120 ohms. So a 120 ohm resistor will give us 100 milliamps. There's one other formula we should write on our bit of paper, and then we're going to print these out and stick them on my bench. Yeah, watts, W equals V times I. Watts equals voltage times current in volts and in amps again. So if we put 100 milliamp load on our power supply at 12 volts, what is the wattage? Well, watts equals 12 times 0.1. 12 times 0.1 is 1.2 watts. So we need a resistor, 120 ohms, and more than 1.2 watts. You could get away with a smaller resistor for a very short period of time, but if we can find something like a 2 watt resistor, let's see what we can find. I don't have any 120 ohm resistors apart from sort of quarter watt ones. So what I've done is I've actually soldered together a 22 ohm and a 100 ohm, just basically using what I have. I mean, the values are not critical, we can always put a different load on. So we can tag our load on here. I'm going to actually just use some crocodile clip leads, that's the easy way to do it. And then let's see if this will provide 100 milliamps on both rails. I've connected the crocodile clip, so it's ready to go. I just tagged another pin header here, so I've got a good ground point. We should just make sure our test setup is good. So if we measure from ground, I can get ground. Well, any of these are ground, to be honest. We can just check. So we should have 120 ohms from here to this crocodile clip. Well, actually, that's reading high. Like I've got a bad connection there somewhere, yeah. We'll check that one. And this one is reading 126. No, it's reading okay. I must have had a bad connection noise. Okay, so we have that. We can now go to volts and let's see what voltage we get out now on our plus and minus supply rails. Okay, so voltage DC. Again, I'll connect to ground. That will do. We can switch it on. And what have we got? 11.3. 10.8. So at 100 milliamps, this transformer is struggling to supply enough voltage. It may be that the input voltage is dropping a little bit too low because we were kind of pushing it. Yeah, we were near to 14 volts coming in, and we probably should be 15 or 16 volts to give a little bit of headroom. Yeah, so you can see that at 100 milliamps it can't really quite supply that current. Now, the ways to fix that, I mean, one would be to get a bigger transformer from some other scrap device. Another would be to, let's say, make a 9 volt supply, plus and minus 9 volts. Then we have a bit more headroom, so we can do that by changing the voltage regulators. But there's another way we can improve the efficiency of this, which might help to get the 100 milliamp output. So let me show that to you and then see what you think. What we have here is basically called a half bridge or a half wave rectifier. Half wave rectifier. So we know that when this end here is positive with respect to ground, which is here, 0 volts, this diode conducts. But the signal coming from the transformer is actually a sine wave, and it's crossing through 0 volts. It's going positive and negative. So when it goes positive here, we see like I drew, we get the positive half cycle, and then the negative one is blocked. And we get the next positive half cycle, and the negative one is blocked. Yeah, continually. So that's what we have here. And the same applies here. So this diode conducts that way, only on the negative half cycle. So when this end here is negative with respect to ground, we get the negative half cycle. So effectively, the positive and negative are only getting a half cycle of the waveform. They're not getting the full waveform. And there's a way we can actually get around that. Or say get around that. There's a way we can make it more efficient. We have the coil. Okay. And we have our diodes. And we have 0 volts. Okay. And we know this end effectively here gets the positive half cycles and this end gets the negative half cycles. Okay. So when this end is positive, the diode conducts. When this end is negative, the diode conducts. But can we make it so that when either end is positive, because they're alternatively positive and negative, it's AC, it conducts? Yeah, we can. So what we can do is this. We can put another diode from here, conducting that way, jump over here, and go to there. Okay, so when this end is positive, this diode conducts. When this end is positive, this diode conducts. So what we've actually got now is we've got both half cycles. So the first half cycle comes through this diode. I'll try and draw it and scale to this so it makes sense. Okay. So the first half cycle comes through this diode. Yeah. And then when this one stops conducting, this one starts conducting. So we get another half cycle through this diode. Yeah. And then back through this one again. And back through this one again. So we're getting twice as many positive pulses. Yeah. From the same transformer. And we can do the same with the negative as well. Yeah. We've got to do the same with both. So we can now take another diode from here this way round. Yeah. We've got to jump over the wire somewhere to there. Okay, so can you see now that when this end is negative, this diode conducts, so we get a negative half cycle. And then when this end goes negative, this diode conducts, and we get another negative half cycle. So again, we get twice as many. If in this case on 50 hertz we were getting 50 pulses a second, we're now getting 100 pulses a second. So more current can flow. Yeah. Now, depending on where the restriction was, if this transformer can't provide more current than it's doing, it may still not give us 100 milliamps. But let's try it because it's interesting. Let's see what happens. I've fitted those other two diodes. I've put some coloured wires to make it a little bit more obvious. So from this end, when this end is the positive end, it conducts through the red wire up to here, the positive voltage rail. And when this end is the negative end, you see the diode there, wired the other way round with a stripe towards the PCB, it feeds a negative down to this voltage rail. So basically now both ends, when they're positive, will connect to here, this capacitor, and both ends, when they're negative, will connect to here, this capacitor. That is called a bridge rectifier, and we now have what is called full wave rectification. So as I showed you, we get twice as many positive and negative pulses basically. Let's connect this up again now, just make sure it's working, then we'll put our load on again and let's see what happens. So we'll switch it on. I'll put my black lead to ground. We now powered on. What do we have? We still have minus 12. And on this one, we still have plus 12. I've reattached the load resistors. Let's just make sure again we have a good connection. So this is 120 ohms and this one is 120 ohms. Let's power it up again now and see if we actually have 12 volts coming out of it. I honestly don't know the answer, guys. I've not tried it, so this is the first time. Let's see. Well, first of all, we better put it onto volts range, hadn't we? That's the first thing. What have we got? 12 volts, yeah? 12 volts. So that's now giving us a stable 12 volts to 100 milliamps. Let's go up again. So let's put another pair of resistors on. Let's see if we can get 200 milliamps out of it. Again, I've gone with what I had lying around. So I found another 100 ohm and another 22, and I put it in parallel with that one. So we now basically have 66 ohms. So this will, we also have some dodgy soldering. Let's just fix that one. Okay. Okay, it's on there. Not brilliant, but it's on there. So we can connect this, and I have another one the same. We can now check, and we should have about 66 ohms, which will give us twice the current. We don't need to really work it out. We know 120 gave us 100 milliamps, so half of that will give us twice the current. Yeah, I mean, you can do the maths if you want. Ohms law, but you'll soon realise that's how it works. So that's there. Again, we will just check to make sure we have a good connection. And then let's see if this can supply plus or minus 12 volts at 200 milliamps. Ohms, ground, 63, 67. It's close enough. It's close enough. Go to DC volts. We'll switch it on again, and let's see if it'll handle the current. Okay, so power's on. What we got? 11.38. 10.9. So it can handle somewhere between 100 and 200. That's what it can handle, and the reason is the transformer. I actually wanted to build this for my milli ohm meter project, the one I published on here. That needs 120 milliamps on the positive supply and 20 on the negative. This is probably good enough for that. But we have a couple more of these transformers in these battery chargers, so let's have a quick look at those as well. Here's one of the other chargers. This one only has the AA and AAA batteries. It's not really very large, this transformer, smaller than the other one, and this will have lower voltages. It doesn't charge the PP3, the 9-volt battery, so that one isn't really of any particular use to us. This is a little, get the PCB out, now it's stuck in there, little surface mount PCB. I wonder if we can see what the chip is on this one, since you've been scraping off all the other ones. Let's have a quick look. Yeah, this one's a CD4060B. This is like the one I repaired that originally got me interested in these chargers. This is a little counter. So basically the way this works is it just uses resistors to limit the current into the batteries. This has a low frequency oscillator that counts up 12 to 14 hours and then turns the output off. That's all it does. It's very, very simple. So it just switches off the charge current to the batteries after 12 to 14 hours time, and the current charging the batteries is purely limited by passing through resistors. Nothing more technical than that. And this is the other one. So this is quite interesting. It has a light bulb, which I've got a feeling is effectively being used as a current limiter rather than just lighting up. It has no active components at all that I can see, just diodes on this side. It has resistor and just other resistors on this side, some resistors here which appear, and these ones also appear to be switched by this switch, some more resistors here. So that literally appears to be just a passive charger. It doesn't seem to have any timer to turn it off or anything like that. This one has the PP3 batteries which were here, or rather the holders were here, and we have 4 diodes in. So I think this is getting like similar to a bridge rectifier. Now if you look at the transformer on this, there's 4 connections, and I think this probably has 2 secondaries. Yeah, 1 secondary here and 1 secondary here. One I think is probably higher voltage than the other one, so one will be the low voltage secondary for these batteries and one will be the higher voltage for the PP3 batteries. And we can figure this out. If we solder our lead with a couple of wires onto here, so we put a bit of power into it, we can measure in AC the voltage coming out of our transformer, and that will give us an idea whether we can actually use this transformer in one of our little power supply projects. I've attached the high voltage wires. Again, this is safe as long as you understand the danger and what you are working on. When I say it's safe, it's not so dangerous as you would think. But depending on your own comfort level and how familiar you are, you could just put a bit of tape over the connections coming in if you're a little bit concerned about them, and then you have a little bit more safety. Just be careful if you do this that the wires don't stick through the tape. Yeah, you could say in actual fact it might be more dangerous to do this because you are now relying on it. Personally, I would rather rely on my own knowledge and experience and understanding. Okay, but if you prefer, there you go. So we can plug this one in. Now we have two secondaries, one here and one here, and they don't appear to be connected together. It's not like a centre tapped winding. So let's see if this is of any use to us. It may be both the same voltage, but I doubt it. Okay, power is on, volts, and we want AC. Yeah, let's plug this one in and see what we have. Okay, what's coming out of our transformer? Well, that's 6.8 volts on it. Yeah. And that's 21 volts on it. So this could be an interesting thing. You won't get a plus and minus volt supply out of it, I don't think. Well, in fact, I'm sure you won't, because I've now switched it off and we can just check. I'm fairly sure we'll find these two windings are separate, and anyway they're different voltages. That's reading quite a low resistance, so it can probably deliver the reasonable amount of current. And this one's reading very high resistance. It's like the other one. The other one was reading about 9 ohms, so it looks like this is providing a higher voltage but at a lower current. Remember that the current that's flowing through your power supply is also flowing through the transformer winding. So that in itself should limit the amount of current the transformer can actually supply. So really, out of the 3 that I bought, only one of them was suitable to make a symmetrical plus and minus supply. And that's a fairly low power one, but I think it's useful enough for little op-amp based projects, things like the milliohm meter. I'm sure we'll quite happily run from that. This one, I think I'll actually use it as a battery charger. Well, if you made it this far, I hope you enjoyed that. If you're a beginner, I hope you've learnt some things here. If you're more experienced, yeah, maybe you've learnt something. There's nothing overly complicated in this, but this is a good way to start learning electronics repair with basics like this. If you get that into your head, I was explaining to you about load impedance and source impedance, you will get a long way with a lot of repairs. I hope you enjoyed it regardless of your experience level, and I hope I'll see you all soon on another Learn Electronics Repair video. Ciao for now, guys.